Hello, everyone. It is great to be back here at the Senate here in Santiago. And today I'm going to step back from the previous two talks and think about our conquest of space from really the beginning of humanity until the present and even into the future. If you think about it, humans have been looking up for the entirety of our lives as a species. And this goes back to the earliest stories that we know of. So if we look up, this is known as the Pleiades, a set of stars that every human that's ever lived has seen. Now, quite remarkably, the Seven Sisters, as this is known in many cultures, is a story that we know of from Greek mythology, but it turns out it is part of Australian indigenous mythology as well, and the story is the same as the Greek story. The interesting part is the Australian indigenous people were separated from the rest of the continent, we believe, around 50,000 years ago. We see the story of the stars in this very famous cave painting in Europe. There are the Pleiades up there. Next, interesting to a bull. Why the bull? Because what is the constellation that the Pleiades are next to? Taurus, the bull. That painting, 17,300 years old. The story of the stars are older than anything else we know. If we go back 2,000 years ago, we were first able, through Ptolemy, to start tracking the planets, something that people cared a lot about in the past, charting the stars so they knew when the seasons would fall, the moving planets being something very mysterious they wanted to understand. And it was just 550 years ago that Copernicus went through and came up with a new idea, an idea with the sun at the center. Now, it turns out it didn't do anything different than the Greek way of predicting the planets, but it was a new way of thinking about the sky, and it was shown to be true by none other than Galileo, who had access to a telescope for the first time. And what he was able to see was that Jupiter, for example, had moons, and Venus had phases. These are things that you could imagine happening under Copernicus' system, but not Ptolemy's. It was also the beginning of science as we know it. Those observations helped Newton create physics as we think of it today. That is some 350 years ago. It allowed us to calculate things. The power of science is not that it's just another philosophy. It is a philosophy that allows us to predict things and to make things. It is what allows us to create buildings that do not fall down, bridges that do not fall down, and of course things like spacecraft or phones that we see in the modern world. It also allows us, when you calculate and predict things, to show things are not right, that you do not have to accept things only on faith, but rather on how well it predicts the future. And if we move forward, we were able to use Galileo's telescope to go out and do things like look at the skies and discover new planets. The planet Uranus, discovered some 250 years ago, thereabouts, going through and scanning the skies, the first planet discovered with modern technology. Going even closer in time, we were able to go through and use the basics of physics, and Einstein, just 100 years ago, was able to rethink how gravity works, to overturn Newton's thinking and create the foundational theory that we all use today. And he did this by making a prediction. His prediction is that space is curved. And when space is curved, weird things happen. For example, if you look at an eclipse, the stars will be bent from where they would otherwise appear. Curved space was this crazy thing that Einstein predicted, and it made him very famous. This is his theory that actually put him on the map 100 years ago, but only 100 years ago. And one of the crazy things it predicts, as I told you, is space that can be curved. That means that when you go from point A to point B, the whole of space, you may travel on a curved path, not dissimilar to what I did coming from Australia to Chile today. I did not do a straight path. I did a curved path down by Antarctica because the Earth is curved. In space, the curvature is in a fourth dimension, rather difficult to visualize, but something we can turn out that we can measure, as I'll show you in a little bit. Soon after Einstein's theory, Hubble was able to go through and use a telescope to go out and measure galaxies. It turns out 100 years ago, we did not even know that galaxies existed. We knew there was something we lived in, the Milky Way, but 100 years ago, we didn't even understand the concept of galaxies. In 1926, Hubble understood galaxies by measuring their distances, and he was able to go out and systematically measure distances to galaxies, and he made a remarkable discovery. The faster the galaxy was moving away from us, measured by how much its light is stretched, we call that redshift, the fainter its stars. And from that, he went out and announced that means that the universe is expanding. And to understand this, let's make a cartoon. Let's take the universe and expand it, and then overlay before and after. And you can see everything moves away from our center, and the nearby things move a little bit, and the distant things, well, they move a lot, just like Hubble saw. 55 years ago, Penzias and Wilson, using this telescope, radio telescope, saw a hiss of radio noise in all directions around the sky. This is the afterglow of the Big Bang. And the Big Bang makes sense because imagine a universe that's expanding. Let's put it in reverse, and what happens? If you put it in reverse, things get closer and closer and closer until everything in the universe is on top of everything else. The Big Bang. Turns out, by our current calculations, that was about 13.8 billion years ago. It was just 50 years ago, this year, that humanity landed on the moon, the first time we were able to really do things off the planet Earth. Interestingly enough, the radio waves were detected where I live now in Australia, just outside of Canberra, a place called Honeysuckle Creek. Think of all that time humanity's been going. Our ability to explore space has happened really in the last 100 years. We've heard earlier from Gaspar about dark matter. The discovery of dark matter is roughly 45 years ago. Being able to see gravity everywhere in the universe, even where there's not mass. Where we think there is something out there that can literally go right through the Earth. We already have a particle that we know exists that's like that, a neutrino, but this has to be something that is 1,000 times more mass in the universe to make it sense. But everywhere we look, we see the signs of dark matter. 23 years ago was the discovery of our first exoplanet. We now have literally tens of thousands of exoplanets. They're everywhere. And my own particular part of this puzzle, 20 years ago, last year, we made our discovery here in Chile of dark energy, and here is the team that won the Nobel Prize with me in 2011. So we'll talk a little bit about dark energy, just so we understand it. It was based on work done up at Cerro Tololo by this Chilean team, and these are people who should be your scientific superstars. And they realized how to use exploding stars called supernovae to measure distances very accurately. And they were part of the team we're all part of, and we went out and we measured, like Hubble did, the expansion rate of the universe. And each one of those bars is a measurement of the expansion rate of the universe. And what we did that was clever is we used the new telescopes and these supernovae that allowed us, that were so bright that we could look very far back into the past, and we could measure how fast the universe was expanding now, and we could measure how fast it was expanding billions of years in the past. And this diagram shows you 8 billion years in the past, the universe was expanding slower in the past and had sped up. That was not what we were expecting. We needed something to push the universe apart, and that is what we call dark energy. I'm sad to say we understand dark energy almost exactly as well today in 2019 as we did in 1998 when we made this discovery. So the universe is accelerating. We're not completely sure why, but the only way we can think of it is space itself is full of energy everywhere, and Einstein's equations tell us that such energy pushes on itself and can accelerate the universe. Over the last 15 years, we've been looking at that hiss of the early universe, the cosmic microwave background. And we've been able to make exquisite measurements. And this is a real measurement. Some of this, again, has been done in Chile. A lot of it's been done in space in Antarctica. And this is a neat experiment because the Big Bang was like throwing rocks into the early universe. And when you make a splash in a pond, the waves bounce around depending on what the pond is made of. And so if you think of Big Bang creating the splash in the pond, which is the universe, you can go through and learn a lot about the universe based on the splash marks, which that is. And so this is how we as scientists look at the splash mark. That bar, actually, that graph tells us essentially how many splashes there are of different sizes. These are big splashes. There's a lot of them of this size. These are littler and littler splashes. And quite remarkable, the theory that tells us about dark matter and dark energy perfectly fits that curve and tells us that for every amount of atom in the universe, there's 6.5 times more dark matter. Those splash marks also have a size, so they allow us, it turns out, to measure the shape of the universe. And that's because if the universe is curved, it magnifies or demagnifies the splashes. And in this case, it turns out when we look at the size of the splash marks, they're exactly the size you expect. If the universe is very boring and not curved at all, but flat, behaves just like your intuition would tell you. In the end, we can put that all together, and we realize that 70% of the universe is dark energy, this stuff we discovered that's pushing the universe apart. 30% is made up of stuff that has gravity that pulls, but only 5% of the entire universe are the atoms we know here in this room and here on Earth. We live in a very funny, messy universe of which what we can measure is a very small part. Now the revolution continues. If you look at 2019, we're building rockets cheaper, faster, and better than ever before. Interestingly enough, it's almost exactly the same basic technology that launched Sputnik in the 50s. But we have better engineering, they're more efficient, but it's fundamentally the same basic idea. But it's not just one or two countries now. Last year, our friends across the Pacific, New Zealand, launched their first commercial rocket, putting up small satellites. And because of miniaturization, which we see embodied in our phones, quite remarkable things can happen in tiny satellites now. Whole navigation systems are being launched from tiny little payloads. And it's not just rockets that are being built. Of course, we're out exploring the solar system. China has just launched and landed a probe on the backside of the moon a few weeks ago. We've been able to explore and look for life on Mars. We have gone through and had the Europeans land on a comet. We have gone through with Cassini and seen geysers of water shooting out of a moon of Saturn, Enceladus. We have been able to go with New Horizons out to Pluto, our most distant non-planet that we knew of when it was launched, when it now has company. And of course, we have just recently, and we're still getting images of this body, the most distant thing we've ever looked at. And the images are coming in, and it is a very odd-looking object, sort of a snowman. This is an asteroid out in what we call the Kuiper Belt, out beyond Pluto. We think it's made of the same type of debris that Pluto was made out of. We are creating observatories that are not just huge telescopes, but tiny little ones that we can put together very cheaply. So here in Chile, we use the telescopes here to look for exploding stars. Now we have little telescopes around the world that are able to look at every piece of the sky all the time, discover all the bright objects. And they're finding all sorts of interesting things. Here's another program called Atlas in Hawaii that was able to find, just in the last year, an object out of the 10,000 exploding stars we had seen. This one's unique. It's much brighter, and it was much faster, and we think it has a completely different energy source than all other objects we've ever seen. We're still trying to understand that. And this capability allows you to do all sorts of interesting things. It allows you to discover objects you just did not know existed. So Oumuamua, which made a lot of headlines, this object is moving very quickly. It's actually on what we call a hyperbolic orbit. That means it has come from beyond the solar system at speed. Quite confusingly, it sped up a little bit as it went around the sun, prompting some people to think this is an alien spacecraft. I'm not yet convinced, but it is a very unusual object, very red, and it turns out very, very oddly shaped. It's the first one we've seen, but we're going to keep on continuing to discover things like this because the fun has just begun. LSST, a giant telescope that a couple years ago we said would look like this picture on the right, is actually beginning to look like that picture on the right. This is an 8-meter telescope that can scan the sky every night to literally 1 billion times fainter than our eyes can see. Who knows what it is going to discover? Turns out planets, as I said, are everywhere. There are literally planets around every star, and there are many, many Earth-like planets. And we can go out with the next generation of satellites and detect Earth-like planets. The idea is that when the planet goes in front of its star, it dims that star and we can see it. But very interestingly enough, here is Venus in front of our sun. You can see that the sun's light is passing through the atmosphere of Venus. And that allows us to see what's in Venus's atmosphere with the next generation of giant telescopes being built, where? Here in Chile. The Giant Magellan Telescope and the extremely large telescope that Catherine just told you about. These telescopes can take the spectra, the colors of the rainbow, and we can identify the atoms that are in the atmosphere, for example, of the planet. And so hydrogen has a very specific signature, sodium, but the really interesting bit is oxygen. Oxygen is hard to imagine being put into a state without life in most cases. We can see potentially life's fingerprint in the atmospheres when they go in front of their stars of Earth-like planets. That's not going to happen 100 years from now. That's going to happen here in Chile over the next 10 to 15 years. And just to let you know, Proxima Centauri, which is about right there, it orbits Alpha Centauri. That's the nearest star to Earth. It has an Earth-like planet. So, it takes 25,000 years to get there with current technology, so probably no time soon, but it is going to be interesting to see what's going on. And these giant telescopes, they're being built here in Chile, and at the same time, we're able to open up new ways to look at the universe, using, for example, gravitational waves, which allowed us to go through and see how black holes warp space, make space a little shorter and longer. This is the signal, tiny, tiny movements, smaller than an atom, that we're sensitive to. And in 2015, we were able to see the first merging black holes and be able to see other things where neutron stars, remnants, the tiny centers of massive stars, came together and created a splash which we believe shows us where gold and uranium and the other heavy elements are made. Always been a mystery. We've always thought they were in normal supernovae. Nope, they're created in the mergers of neutron stars. And the black holes are really remarkable. The black holes that this experiment is seeing are huge. Some of them are upwards of 30, 40, 50 times the mass of our sun. We've never known these things existed. Why these things exist? Well, still being determined. But again, this is the tip of the iceberg. Because when we look back to the early universe, we see huge, billion solar mass black holes right after the Big Bang. Why are they there? We do not know. It makes no sense. With these big telescopes right now with the Hubble, we can look back to these are the most distant galaxies we know. They occurred about 500 million years after the Big Bang. With the big telescopes and James Webb Space Telescope, we're going to be able to look back even further, being able to look at the first stars as they formed, hopefully the first black holes as they formed, be able to sort together the story of our universe. The universe in 2019 is still rich with mystery. From our solar system to the most distant objects in the universe, from understanding Earth-like planets to black holes, we really have a lot to do. My area of cosmology, dark matter, dark energy, 95% of the universe remain a complete mystery in 2019, despite us understanding them now for between 20 and 40 years, the existence of this stuff. The solution from new ideas powered by the observations of new telescopes, and Chile will be in the middle of it all. Thank you very much.